We've looked at Boyle's law in pretty great depth. Now we're going to go a little bit faster through Charles' law, the next law. This is a relationship between volume and temperature. So the other two variables, amount of gas and pressure, are going to be held constant. So here's what Charles' law states. The volume of a fixed amount of gas held at a constant pressure varies directly with the temperature. Here's what this would look like graphically. If we plot temperature versus volume, we will find a straight line relationship. That's called a direct proportionality. When the temperature gets bigger, the volume gets bigger. Most of us have an intuitive feel for this. You heat up a balloon and it expands. But if you actually put it to experiment and collect some data, you will find out that it's a straight line relationship. And straight lines, of course, are y equals mx plus b. That's the algebraic way to describe them. Y here is volume, and m is just the slope of the line, some constant we'll call k. On the x-axis, we're plotting temperature, and then plus b. Now, scientists have a problem. It's harder to do math with an equation like this than with an equation that doesn't have a b. If b was 0, then we'd be okay. We could use a simple proportion to solve these kinds of problems. But it isn't. And the fact that temperature can be negative in the Celsius scale, if we're plotting Celsius or Fahrenheit for that matter, on the x-axis, we'll find out that we're going to have numbers that are below 0, -1, -2, and so on, because 0 isn't the lowest possible temperature in that scale. So what scientists have done is they've estimated what's the lowest possible temperature you can get by extending the straight line that you get out farther until it crosses the temperature axis. And what they found out is at about 273 below 0 Celsius, you get the coldest possible temperature that there could possibly be. Well, that represents 0 on a different temperature scale that we've looked at earlier in the year, and that's the Kelvin temperature scale. So if I plot temperature in kelvins on the x-axis and volume on the y-axis, my line goes right through 0, 0. And so y equals mx plus b, or v equals kt plus b, turns into just v equals kt. And that's very handy mathematically. So how do we convert between Kelvin temperatures and Celsius temperatures? Because we're going to have to do this if we use this law. Here's how you do it. If I have the temperature and it's in Celsius, if I add 273 to it, I will get the temperature in kelvins. So for example, say it's 25 degrees C. Add 273. That tells me that my temperature is 298 kelvins. And it's not called degrees Kelvin, it's just called kelvins. If I had to go the other way, my temperature in Kelvin minus 273 would give me my temperature in Celsius. The actual number here isn't 273, it's actually 273.15, but most of the time 273 is going to give us enough significant figures for what we're doing. So let's develop a two-point relationship. Thinking about the graph where we've got temperature in kelvins and volume on the y-axis, remember the straight line relationship goes like this. Think about 2 points on this line, point number 1 and point number 2. It represents same pressure, same number of moles of gas. At point 1 we have temperature 1 and volume 1. At point 2 we have temperature 2 and volume 2. Well, the relationship, remember, is volume is a constant number times temperature. So to find out what the constant is, it's just volume divided by temperature is constant. So that means at point number 1, V1 over T1 is the constant. At point number 2, V2 over T2 is the constant number. But since they're both equal to the same constant, that means V1 over T1 is equal to V2 over T2. And there's the two-point form of Charles's law. This is a simple proportion. Cross multiply and divide to find the missing variable. That's a lot easier than dealing with a b in your equation, a y-intercept in your equation. And so that's why we always use Kelvin temperatures. Like in this problem. It says the volume of a balloon at negative 34 degrees C is 0.250 liters. If the pressure is constant, what would be the balloon's volume when the temperature is 25 degrees C? So here we go. Volume 1 over temperature 1 is volume 2 over temperature 2. Let's put numbers in here. The first volume is 0.250 liters. The first temperature is 34 below Celsius, but I can't use Celsius here. I've got to use kelvins. So I'll take negative 34 and I'll add 273 to it. What I get is 239 kelvins. What I'm trying to find here is V2. What is the balloon's volume is the question. The temperature is 25 degrees C. That's T2. If I add 25 and 273, I find out that I have 298 kelvins. Now to find V2, it's a simple matter of cross multiply and divide. 298 times 0.250 divided by 239 gives me V2. And V2 is 0.312 liters. Kelvins have dropped out, so that's why I have liters as a volume. Now you can ask yourself, does this make sense? The temperature went up, the volume also went up. So yeah, that does follow our rule. You try one. Stop the video, try and work it out. I'll provide you with an answer in a bit. So in this situation, we could set it up this way. We could say volume in the room over temperature in the room is equal to volume outside over temperature outside. And what we're trying to find here is what's the volume outside. Let's just put numbers in here. Volume in the room is 1.50 liters. The temperature in the room is 25 degrees C. But we can't put degrees C in here. We have to put kelvins in. 25 plus 273 gives me 298 kelvins. Volume outside is what I'm trying to find. And the temperature outside is 38 degrees Celsius. But I can't put in Celsius. I need to add 273 to get Kelvin temperatures. And when I do that, I find out that I have 311 kelvins. Now to find my answer, I cross multiply and divide. So I take 311 times 1.5. I divide that by 298. My answer is going to be in liters, and volume outside is 1.56 liters. Temperature went up, volume went up. That seems to make sense. Well, there's another law, Lintons Law, that relates pressure and temperature. So we've looked at pressure and volume, that's Boyle's law. We've looked at volume and temperature, that's Charles's law. And Lintons Law looks at pressure versus temperature, and so that means the other two variables have to be held constant. So here's the statement of the law. The pressure of a fixed amount of gas held at a constant volume varies directly with the temperature. Graphically, here's what that looks like. Again, I'm going to use Kelvin temperatures here. Starting with Kelvin temperatures at 0, as the temperature gets bigger, the pressure gets bigger, and it's a direct proportionality. So, straight line, y equals mx plus b, but there's no b here because b is 0. Y-axis is p, a constant number, that's the slope, is m, and temperature in kelvins is x. So mathematically, here's how we would write it. Pressure is equal to a constant number times temperature. Thinking about a two-point form, well, pressure is constant times temperature. So pressure divided by temperature is constant. And just like we saw for Charles' law, the two-point form is going to look like this. One pressure divided by its temperature is equal to any other pressure divided by its temperature. So there's the two-point form of Lintons Law. You can use it for solving problems like this. Let's try it. Pressure in a bike tire is 115 psi at 25 degrees C. So P1 over T1 equals P2 over T2. And we're supposed to find out what's P2. Let's put numbers in here. P1 is 115 psi, pounds per square inch. T1 is 25 degrees C. Well, that's 298 kelvins if you add 273 to 25 degrees C. P2 is our unknown, and our second temperature is 18 below 0 Celsius. So if I take negative 18 and add 273 to it, I get 255 kelvins. Now I cross multiply and divide. 255 times 115 divided by 298. Kelvins drop out, and I find my second pressure is equal to 98.4 pounds per square inch. You try this one. Stop the video and try and work it out. I'll give you an answer in a minute. Pressure 1 over temperature 1 is pressure 2 over temperature 2. Volume doesn't change, so this law is valid. Now, we're looking for T2. That's the missing thing here. Let's put in the other quantities. The pressure at condition 1 is 4.3 atmospheres. And that's when the temperature is 150 degrees Celsius. Well, 150 degrees Celsius is 423 kelvins. Add 150 and 273 to get that. The second pressure is 4.4 atmospheres, and T2 is our unknown. Well, we cross multiply and divide to find our answer. 4.4 times 423 divided by 4.3 gives us T2, and the atmospheres have canceled out, so T2 will be in kelvins, and the answer is 433 kelvins. If we wanted to know that in Celsius, we could just subtract 273, and you'd find out that the temperature is 160 degrees C. Well, here's what we know so far. We know that volume is equal to a constant number times temperature. So when temperature goes up, volume goes up. We also know that volume is equal to a constant number times 1 over pressure. So when pressure goes up, volume goes down. So if we were to put these two relationships together, we should find that volume is equal to some different constant number times the ratio of temperature to pressure. So mathematically, we'll make this statement. Volume is equal to a constant number times the ratio of temperature to pressure. To make that into a two-point form, starting from volume is equal to K times T over P, multiplying both sides by pressure gives us this relationship. Pressure times volume is a constant number times temperature. But if we divide both sides by temperature, temperature drops out and we get this. Pressure times volume divided by temperature is constant. So that means the pressure, volume, and temperature at one condition will have P1 V1 over T1 equal to the same constant that is P2 times V2 over T2 for a different condition. And so this is the two-point form of the combined gas law. Now, the combined gas law is really useful because the only thing that has to stay the same is the number of moles. Pressure, volume, and temperature can all three change at once, and this allows us to solve for the missing variable. Here's an example of a problem like this. Weather balloon has a volume of 5,000 liters when the temperature is 28 degrees Celsius and the pressure is 754 millimeters of mercury. So that's a P1, a V1, and a T1. Then we're supposed to find its volume, V2, under different conditions. When the pressure is 0.3 atmospheres, that'd be P2, and the temperature is 25 below Celsius, and that'd be T2. Well, we can put the numbers in here just like we would if it was Charles' law or Boyle's law. P1, 754 millimeters of mercury. First volume is 5,000 liters. T1 is 28 degrees Celsius. Well, 28 degrees Celsius is 301 kelvins, and remember we have to use kelvins in these gas laws. P2 is 0.3 atmospheres. Now that's a problem, because I can't put 0.3 atmospheres in here and expect my units to cancel, because my other pressure is in millimeters of mercury. So I'm going to do a little conversion off to the side here. 0.300 atmospheres, I want to convert that into millimeters of mercury. Here's what I know. 1 atmosphere is 760 millimeters of mercury. So here's the conversion. 228 millimeters of mercury is 0.3 atmospheres. So that's what I'm going to put in here. 228 millimeters of mercury. V2 is what I'm trying to find. and T2 is 25 below Celsius. Well, if I take negative 25 and I add 273 to it, I'll get 248 kelvins. All right, now I can cross multiply and divide to get my answer. 754 millimeters of mercury times 5,000 liters times 248 kelvins will be equal to 301 kelvins times 228 millimeters of mercury times V2. So to solve for V2, I'm just going to divide both sides by the product of 301 kelvins and 228 millimeters of mercury. Look what will happen to the units. Kelvins will drop out, pressure units will drop out, millimeters of mercury, and V2 will come out in liters. Here's what the answer is. It's 13,600 liters. It's a little harder to check your answer here because with all these variables changing, it's harder to have an intuitive feel for what's right. You try this one. Stop the video, try and work it out. I'll give you an answer. Well, we could set this up this way. We could say pressure on the beach times volume on the beach over temperature on the beach is equal to pressure on the mountain times volume on the mountain divided by temperature on the mountain. Put in the information that we have. The pressure on the beach is 760 millimeters of mercury, or 760 torrs. The volume on the beach, it says, is 1 liter. Temperature on the beach is 30 degrees C. If I add 30 to 273, I will get 303 kelvins. Pressure on the top of the mountain is 400 millimeters of mercury. The volume up on the top of the mountain is 1.6 liters, and the temperature on the top of the mountain is the part we don't know. So let's cross multiply and divide. Multiplying this diagonal, we get 400 millimeters of mercury times 1.6 liters times 303 kelvins equals the other diagonal, which is 760 millimeters of mercury times 1 liter times the temperature on top of the mountain. So we'll solve by dividing both sides by 760 millimeters of mercury times 1.0 liters, and that'll cancel that out on this side. But over here, when we divide by 760 millimeters of mercury and 1.0 liters, the only thing that cancels out is the units, liters and millimeters of mercury, which tells us Tm in kelvins. So we'll do our arithmetic. 400 times 1.6 times 303 divided by the product of 760 times 1. Well, it gives us 255. We really only have two significant figures, so we'll round it to 260 kelvins. And if we subtract the 273, we find that temperature turns out to be below 0 Celsius. Not uncommon on a mountaintop.